Welcome to our ongoing series of discussions of Titelbaum chapters and the homework for each of them. Today we're doing chapter 2 in the Titelbaum book. Now I am going to be pausing between problems for the most part because, as I said already, the final take-home exam is going to be in large part taken from the homework in the Titelbaum book. So the homework problems that are going to be on the final, I need to skip. That's going to require that I pause and skip 2.4, 2.6, a couple parts of 2.6 and 2.9. So let's get started. We're now talking about state descriptions, which is just a fancy word for lines on a truth table when we're talking about probability theory, because it's right now just a propositional theory. So a state description is just a complete set of truth value assignments for each of the atomic sentences in a language, and you'll recognize that as just being the same thing as a line on the long truth table. So problem 2.1 begins by asking us to list all 8 state descriptions available in a language with 3 atomic sentences, P, Q, and R. You already know how to construct the long truth table for any sequent involving those 3 sentence letters. The number of lines on a truth table is 2 to the n, where n is the number of atomic sentence letters involved. So if there's 3 atomic sentence letters, there are 8 state descriptions. So the answer to the first one is, you can construct the truth table if you want, but I just point out a simple truth table gives this information. And then in answering B, I actually construct the truth table. So we're supposed to give the disjunctive normal form of P or Q implies R. So first, construct a truth table. Now, what I did here, I construct a truth table. So the first thing I do is the first 3 columns are the columns that give the information you needed to answer A. So if you wanted to just construct the first 3 columns as your answer to A, that would be a perfectly adequate answer. You could also just say true, 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 false, true, false, true. You could do it that way individually for the P, Q, and R, and the answer would be perfectly fine. Then what I did at D, since I'm supposed to be constructing the truth table to give me the truth value for the horseshoe, I first need to know what's the truth value for the disjunction. So column D calculates the truth value for the disjunction P or Q from the truth values for P, Q, and R respectively. In this case, all you needed was columns A or B. And then I use the truth value in column D to calculate the truth value for column E, which is the truth value of the horseshoe. It takes as input the truth value for column D combined with the truth value for R. So that's the table that I constructed in order to answer this problem. That tells you what the truth value is for the horseshoe formula for each of the state descriptions. And you can see there are 2 of the 8 state descriptions where it comes out false, and 6 out of the 8 come out true. That shouldn't surprise us because an arrow formula, there are 3 ways of it coming out true and 1 way of it coming out false. So we should expect 75% of the complete truth table to come out true for any arrow formula and 25% to come out false. All right, the last concept here in the question is this concept of disjunctive normal form, which we didn't talk about when we did logic. But here's the fact. In propositional logic, every proposition whatsoever has a logically equivalent disjunction. How do we get this disjunction? Well, you construct the truth table for the formula you're looking for, and then you identify the lines on the truth table where it comes out true. Rather than draw arrows, I'll just draw a line to identify them. You identify the lines where it comes out true, and then you say, this proposition is equal to a disjunction of P and Q and R, that's line 1, or P and not Q and R, that's line 3, or P and not Q and not R, that's line 4, or not P and Q and R, or not P and not Q and R, or not all three. That's how you construct the disjunctive normal form of any proposition whatsoever. Just do the big long truth table for the formula that you're looking at, identify the lines of the truth table where it comes out true, and disjoin those lines. That is the disjunctive normal form. So that makes our disjunctive normal form a disjunction of the combined truth values for P, Q, and R at lines 1, 3, 4, 5, 7, and 8. We thus get, and then I wrote it out by hand. I wrote it out rather than just reading it off for you. That's the 6 lines of the truth table with the relevant truth values for P, Q, and R. Disjunctive normal form is going to turn out to be a useful tool to remember, because sometimes when you're calculating the probability of a claim and you're not sure exactly how to do it, you might be able to figure out, say, what the truth value of combinations of claims is, even though you can't quite figure out what, say, the probability of P or Q is. But if you know what the probability of each of the big, long combined claims that are conjunctions, and you can calculate, you can factor what the disjunctive normal form is, you might be able to get some help solving problems. So disjunctive normal form is not just a technical term that we define just because we can, but it turns out to be useful, and you will see this pop up in some homework later on. In fact, it will pop up in a proof. The proof of our general disjunction rule will employ a version of disjunctive normal form in the proof itself. Okay, 2.2 we're fine about. It's not on the exam. So he starts out by making a fact, telling us a fact, not making one. For any non-contradictory propositions X and Y, X models Y if and only if every disjunct in the disjunctive normal form equivalent of X is also a disjunct of the disjunctive normal form equivalent of Y. Okay, that's a fact. Use this fact to show that P or Q and R entails if P or Q, then R. Now, I hope you can look at that problem and see that it has to be true, because this is a stronger claim than this. This premise says that both the antecedent and the consequent of our conclusion is true. The conclusion only says that either the antecedent is false or the consequent is true. So the entailment holds, but let's try to use the fact to fact about disjunctive normal form equivalence to demonstrate it. So first, let's do a truth table. Now, I did a redundant column here because H is the column which is the conclusion. It adverts to column D, which is the antecedent of that. And then I just duplicated D as G to make it easier for me to see visually, because I want the values in D combined with the values in R. And I think I was thinking it'd be easier to see if I put them over on this side. It turns out it actually made it harder to see, but that's okay. So I do the truth table and then figure out whether the subset claim that's in the fact is sustained. And I put a check mark in every column where it was sustained. I put a check mark every time there wasn't a counterexample to the subset claim. Okay, now the only lines that are going to count, of course, for the disjunctive normal form are lines where the formulas in question come out true. So for the premise, the lines in the disjunctive normal form, I'm going to get my little marker. The lines in the disjunctive normal form for the premise are 1, 3, and 5 only. And notice, as we saw before, the lines in the disjunctive normal form for the conclusion are 1, 3, 5, 7, and 8. So notice what the claim was. Every disjunct in the disjunctive normal form of the premise is also a disjunct of the disjunctive normal form of the conclusion. So we had 1, 3, and 5, and notice all of those are in the disjunctive normal form of the conclusion. So all the lines check out. There aren't any counterexamples arising from the claim. In some cases, because, for example, if you have a false premise, you aren't going to get a counterexample to the claim. The disjunctive normal form for the premise includes the conjunctive truth values for P, Q, and R at lines 1, 3, and 5. That's from column E. The disjunctive normal form for the conclusion involves 1, 3, 5, 7, and 8, as we just went over. Since 1, 3, and 5 are included in 1, 3, 5, 7, and 8, that's what we were asked to show. Explain why the fact is true. Now, I started to do that right here. If the first weren't a subset of the second, we'd have a case, we'd have a line on the truth table where the premise is true while the conclusion is false, thus invalidating the claim of semantic conflict. For the if direction, if the first is a subset of the second, there can't be cases where the second is false, second formula is false, but the first is true. That's what it is for the second to be a semantic consequence of the first. For the other direction, assume that the second is a semantic consequence of the first, but that the subset claim is false. If the subset claim is false, there'll be at least one line on the truth table where the premise holds but the conclusion doesn't, and that contradicts the semantic consequence assumption. Okay, problem 2.3 is just a fun kind of proposition to try to explain and defend. So explain why a language within atomic propositions contains this many non-equivalent propositions. And then he gives us a hint. Now this one is a rather daunting one to try to figure out, but where you can start with is, you know how many state descriptions there will be available for a language within atomic propositions. It's just 2 to the power of n, because that's the number of lines on the big long truth table. And then all you have to do is think about all the possible ways of combining into disjunctive forms all of the 2 to the n lines on the truth table. So here's one way to understand how to do that. So we start out with anatomic formulas. So we get independent claims by considering for any number m less than or equal to n, how many ways there are for a truth table to have m lines come out true. Okay, now non-equivalent propositions will have different combinations of lines coming out true on the truth table. So if we consider all of the different ways of having m number of lines come out true on the truth table, we can sum them up and figure out how many non-equivalent propositions there are. So consider a simple example. Suppose our truth table has 4 lines, then n equals 2. And we get 16 possible results for the possible values of m. Remember, m is any number less than or equal to n. So where m is 4, there's exactly one way for that to happen. Same where m is 0. So let the disjunctive normal form for a sentence be one where it comes out true on all 4 lines. There's only one way for that to happen. And let a contradiction be one where m equals 0. No lines of the truth table come out true. And there's only one non-equivalent contradictory proposition. Because remember, every contradiction is logically equivalent to every other one. So remember, we're looking for non-equivalent propositions. All right, so that leaves us with 3 other possibilities. M can be 1, 2, or 3. And where m is either 1 or 3, there are 4 ways for each of those to happen, because there are 4 possible slots for the single T or F to be placed on the truth table. Where m is 2, there are 6 ways for truths to show up on the truth table at lines 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and at 3 and 4. Sum all of those possibilities and you get 16 different possible combinations of truth values for the 4 lines. So where there are x number of lines on a long truth table, the total possible combinations are x squared, where x is the number of lines and the value for n is 2. So x equals 2 to the power of n, and hence x squared is 2 to the power of 2 to the n power. Okay, 2.5 says, can a probabilistic credence distribution assign credence to p of 0.5, credence to q of 0.5, and credence to not p and not q at 0.8? Explain why or why not. Now, it's important here that the credence distribution is a probability function. So it has to obey all of the axioms of the probability calculus. So here's some stuff that we know from the probability calculus. If the credence for p is 0.5, then of course the credence for not p is 0.5. And if the credence for q is 0.5, the credence for not q is 0.5. Both of those follow from the negation rule. We also know that the probability of a conjunction is the probability of the first times the probability of the second given the first. So in particular, the probability here is going to be the probability of not p times the probability of not q given not p. That's the next sentence. So the probability of our conjunctive credence is going to be the credence of the first times the credence of the second given the first. Now, we know that the first number here is 0.5. We also know that the second number can't exceed 1, because no probability of any sort ever has a probability higher than 1. So the maximum value for the conjunction is going to be 0.5. Thus, the answer to the question is no, you can't have this credence if you have the first 2 credences. All right, now 2.6, there are 2 claims that we're gonna do some proofs here of probability theorems. And I'm gonna take them in a certain order, and 2 of them I'm gonna leave out and they will be on your take-home final. One is the entailment principle, and one is the decomposition theorem. So I will stop sharing when we get to those. So here are the axioms in Titelbaum: non-negativity, normality, and finite additivity. And here are the theorems. So the first one, negation, we will do. I'm only going to skip entailment and decomposition. So how do we prove negation? The negation claim is for any proposition in our language, the credence of not P is 1 minus the credence of P. All right, here's what we're going to do. First, note that P and not P are mutually exclusive. That's simply a logic fact. So by finite additivity, we can calculate their probability by summing the probability of each. Good. Third claim. I was hoping I could scroll down only one at a time, but that's not going to work. Note as well, P or not P is a tautology. So we can, by normality, conclude that its credence has to be 1. And that means if we substitute what we had at line 2 into this formula, we get that I switched order, but 1 is the credence of P plus the credence of not P. And then by simple subtraction, that shows that the credence of not P is 1 minus the credence of P. So that's a straightforward proof, and notice there are some logic facts that we have to know in order to apply the axioms. You have to know what's a tautology, and you have to know what it is for propositions to be mutually exclusive. And that's not part of probability theory, that's just part of logic more generally. Okay, that's a proof of negation. That's probably the easiest theorem to prove about the probability calculus. Okay, I'm scrolling down slow so that I don't make a mistake and go too far. Second, we're supposed to prove maximality. For any proposition, its credence is less than or equal to 1. Nothing exceeds a probability of 1. So I say, suppose there is a proposition P with probability greater than 1. So suppose maximality is false. By negation, its denial would have to have a probability less than 0, which violates the non-negativity axiom. Remember, non-negativity says no proposition has a probability of less than 0. So notice, once we prove negation, we can use negation in the process of proving other theorems, in this case, maximality. So maximality is a super quick theorem to prove once you have negation. Notice you could have done it in the other direction as well. You can give a proof that looks a mirror image of the proof for negation, and then you could use maximality to prove the negation rule if you wanted. Okay, the next one is contradiction. For any contradiction F in the language, the credence for F has to be 0. Okay, now this one I already adverted to in the homework for, I believe, chapter 1. And I am going to do what I did there, which is give you an explanation that appeals to the logical equivalence theorem, which we haven't proven yet. And then just tell you, once we prove logical equivalence, you will be able to derive contradiction from that. So this is not technically a proof because we haven't proven logical equivalence yet, but as soon as we have, this will be a proof. So anyway, a contradiction is a statement of this form, a conjunction of a claim and its negation. So take any statement of this form. By finite additivity together with normality, the probability of phi or not phi is 1. And we know that phi or not phi is logically equivalent to the negation of not phi and phi by De Morgan's rule from the propositional calculus. So if we can prove equivalence below, we can show that the probability of the negation of not phi and phi is 1. as well as that the probability of the negation of the conjuncts in the other order is 1, since conjunctions commute. So if we appeal to equivalence once more after commutation, the probabilities have to be the same. Then using this last probability and applying the negation rule, we get that the probability of phi and not phi is 0. So let's wait to see what the proof of equivalence looks like before. But once we have it, then the fact that we can convert propositions into equivalent propositions shows that we can get that the contradiction, that any contradiction has to have a probability of 0. All right, now entailment is one of those that's going to be on the take-home final. So I'm going to stop sharing and scroll down past it. And I hope I don't screw this up, because if I do, you just got to look at my answer, which is probably going to be good enough to get credit for on the final, so long as I don't have a mistake in it. But I think I did that right. And we're jumping, whoops, I paused it accidentally. We're jumping straight now to the equivalence claim that I said we needed, or we didn't need it, but we used it to prove the last theorem that we were talking about, that all contradictions have a probability of 0. So let's talk about equivalence. Take any two propositions that are equivalent, then their credence has to be the same. So start out assuming that the two are equivalent. If so, it will be a theorem that not A or B is true. Now, let me explain why that's true. I say because of the deduction theorem and the wedge arrow rule. So let's see why that's true. The deduction theorem says if you can prove B on the basis of A, then A arrow B is a theorem, provable from no premises whatsoever. Okay, so take for granted the deduction theorem and then convert this formula by the wedge arrow rule, and you get not A or B. And that too will be a theorem. Okay, so that's the first step of the proof. We now have a theorem given the assumption that we made. Okay, by the assumption, this claim, this disjunction is exclusive, right? If A and B are interderivable, at most one of A or B is false. They have to have, this basically says they have to have the same truth value. So if you disjoin B with the denial of the other, or vice versa, you're going to have a disjunction that's exclusive. So its probability is the probability of not A plus the probability of B by finite additivity. Moreover, this disjunction is a tautology. That's what it means to say it's a theorem, since it can be proven from no premises whatsoever by assumption. So its sum has to be 1. This sum has to be 1 by the normality axiom. So the probability of B is 1 minus the probability of not A, just by simple subtraction. Now, we've already proven that the probability of X is 1 minus the probability of X. So look at this sequence of equivalences. We start out here with the first one. Probability of B is 1 minus the probability of not A. And then we replace, whoops, let me clear that. Then we replace the probability of not A using this. We replace the probability of not A with 1 minus the probability of A. So we start out, probability of B is 1 minus the probability of not A, which is the same as 1 minus 1 minus the probability of A, which is just the probability of A. So the probability of B just is the probability of A, given this assumption. Okay, general additivity is not going to be on the take-home final. So here's the general rule for dealing with disjunctions when you don't know, when they aren't mutually exclusive. If they are mutually exclusive, you can just add. If they're not mutually exclusive, you first add and then subtract the combination of the two. So let's try to see how to prove that. And here's where we're going to start. First, as I emphasized earlier, it is often useful to construct logical expansions of claims when you're trying to do proofs about them. So the first thing I'm going to do is do a logical expansion both for A and for B. So A is equivalent to A and B, or A and not B. And B is equivalent to A and B, or not A and not B. Okay, so we start out with the expansion, and then we note that the disjunctions here are exclusive disjunctions. So we can get the probability of A just by summing the probability of the first disjunct plus the probability of the second disjunct. And we can do that for both the probability of A and the probability of B. Notice then that tells us that the probability of A plus the probability of B is the probability of A and B plus the probability of A and not B. That's the probability of A, plus the probability of A and B plus the probability of not A and B. That's the probability of B. Now subtract one of the probabilities of A and B from both sides. Notice it occurs twice on this side. So take one of them away, and then you get that the probability of A plus the probability of B minus the probability of A and B is the sum of these three things. All right, now when I was talking about disjunctive normal forms for propositions, I said we would use something about disjunctive normal forms when it came time to prove the general additivity rule, and that's where we now are. What I want you to notice is the disjunctive normal form of A or B is just these three lines on the truth table. There are three ways for A or B to be true, and one way for it to be false. The way for it to be false is for both of them to be false. And notice that conjunction, and that conjunction are the three ways in which A or B comes out true. The only one that's not included there is the not A and not B line of the truth table. So note that A or B is logically equivalent to the disjunction of those three lines of the truth table. That is the disjunctive normal form of that disjunction. Note as well that these three disjuncts are all mutually exclusive. Notice that's true of every state description. Every line on a truth table is mutually exclusive of every other line on the truth table. It's designed to be that way. So add the probability. So add to get the probability by two applications of finite additivity. So turn this into a plus sign and that into a plus sign. And then that's this line above it. That's the right side of the previous equation, and thus the right side of the previous equation also gives us the probability of A or B, since they are logically equivalent, and logically equivalent propositions have the same probability. So the probability of A plus the probability of B minus the probability of A and B just is the probability of A or B. That's a proof of the general disjunction rule. All right, the next proof is the finite additivity extended proof. And Mike proved that in the textbook. And I have duplicated his proof here, but there's no reason to go over it because it is nothing more than copied and pasted from the text. I may have switched some margins around or something, but I don't think so. I think I just copied and pasted and made sure the formatting looked the same. Okay, so you can read that from the textbook. You don't need me to read it back to you. So partition says this: for any finite partition of propositions in a language, the sum of their unconditional credence values is 1. Now, recall what a partition is. I prefer to think of, if I can get my little note taker, I call it a block of cheese. Logical space is always, for me, a block of cheese. If you want to call it something else, call it a bar of gold, I don't care what it is. That's our total probability space. And a partition is a way of cutting it into pieces. So you partition it by cutting it into pieces in a way that exhausts the space and doesn't have any overlap between compartments. So that's a partition into 2 parts. That's a partition into 4 parts. If I make sure that the lines connect. But it doesn't matter how you carve this space up. You could do it like this. And you'd also have a partition. It has a whole bunch more compartments now than our earlier ones, but it's just a way of carving up the space. So here you'd have 1, 2, 3. This is part of the second space. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, this is a partition of 15 compartments. And notice none of the compartments overlap and they all exhaust the logical space in question. So what we're supposed to prove here is that latter fact, that the partitions sum in their unconditional credence values to 1. So here's what I write. A partition is a way of dividing a space so that the individual units that yield the partition are exclusive and exhaustive. The totality of the units exhausts the space, and each unit within the partition is incompatible with every other unit in the partition. But if logical space is exhausted by such a partition, then the disjunction of all of the units is a tautology. You're either in unit 1 or 2 or 3 or n. So its probability has to be 1. And since every unit is exclusive of every other, we can, by finite additivity, generate this value of 1 by adding together the individual probabilities for each of the units. So the sum has to be 1, as partition claims. Okay, that's a relatively simple idea, and all you have to do is understand the concept of a partition to see that it has to be true. Okay, problem 2.7. This is about converting between odds claims and probabilities. So it's a relatively lightweight kind of question. So C3PO tells Han Solo that the odds are 3,720 to 1. It'd be interesting to know where in the world that number comes from. It's sort of like when we had sports in America, ESPN was always posting probabilities of winning as the football games progress. So you're up by 2 touchdowns with 3 minutes left, and there's a 98% chance you're going to win. Be interesting to know what in the world the statistical basis is for such claims. But in any case, C3PO has some pretty precise numbers. So all you do to convert to a probability is sum the 2 parts of the odds, comparisons, and put the second one over the first. So the probability is 1 over 3721. Now, B says, suppose C3PO is certain that they will survive if they either successfully navigate the asteroid field or fail to navigate it, and hide in a cave. He's also certain that those are the only two ways they can survive, and his odds against unsuccessfully navigating and hiding in a cave are 59 to 2. Assuming his credences obey the probability axioms, what are his odds against their surviving? Well, you sum 1 over 3721 plus 2 over 61, get a number, turn that into a fraction if you want, and then convert it back to an odds claim. The easiest thing is to take 2 over the product of the denominators, and then just subtract 2 from the denominator and do the odds thing that way. I didn't do that for you. It looks like it's such a simple thing. You can do the math yourself. And then I got tired of answering stupid questions about The Empire Strikes Back. So apparently Han responds to 3PO's odds declaration in a certain way. And I guess you'd have to go back and watch the movie or watch that part of the movie to find out what he had to say. And I lost patience. So I said, I'm not going to answer that. All right. Problem 2.8 is not going to be on the exam. So look at this credence table. You have a credence table over propositions P, Q, and R, generates 8 state descriptions, and then some of the lines have non-zero credences and some have 0 credences. Okay, then we're supposed to use this table to calculate the following values. What's the credence that P is equivalent to Q? The answer is 0.4. So where did I get that answer? Let me see if I can get my little annotator. Well, P is equivalent to Q comes out true on this truth table when P and Q have the same truth value. So they have the same truth value at lines 1 and 2 and 7 and 8. The middle 4, they have opposite truth values. Okay, so you calculate the credence for it just by summing 1, 2, 7, and 8, and the answer for that is 0.4. What's the credence for if R then Q? Answer is 1. How do I get that? Well, you look at all of the lines where either the antecedent is false or the consequent is true. So that will get us false, 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 true. We already have that one. True. And we already have that one. So you're going to sum everything at lines I just circled it backwards, didn't I? Let me start that one over. Clear all my drawings. So let's pick all of the lines where R is false. That would be line 2, 4, 6, and 8. Then also pick all of the lines where Q is true. That's 1, 2, 5, and 6. So which lines are left out? Line 3 is left out. Line 7 is left out. So that means we sum all the other lines, and that sums to 1. So the credence for that is 1. How about the credence of P and R minus the credence of not P and R? And that's 0.1 minus 0.1, which is 0. And I think by now you can look at to see which lines both P and R are true, and lines where P is false but R is true, and see that they sum to 1 in each case. Okay, the only new thing is a conditional credence. Well, not a conditional, but a fraction. What's the credence of P and Q and R divided by the credence of R? Well, there's only one line where P, Q, and R are all true. That's the first line. So 0.1 is our value in the numerator. Now, what's the credence for the lines where R is true? Well, that's 1, 3, 5, and 7. 3 and 7 have 0, but 1 and 5 have 0.1 each, so our denominator is 0.2, and that's 1/2. Okay, yeah, problem 2.9 is going to be on the final, so I will skip that one. And then we pick up on problem 210 with the really interesting psychological research on probabilistic reasoning. So Tversky and Kahneman are famous for conducting experiments where they find that ordinary subjects commit the conjunction fallacy. And their results have held up to replication quite widely. So the conjunction fallacy is where you assign a higher probability to a conjunction than you do to one of the conjuncts. And that can't happen because remember the entailment claim. If A entails B, then your probability for B needs to be at least as high as your probability for A. So if something is a red car, it's a car, and your probability that it's a car has to be at least as high as your probability that it's a red car. Now, the conjunction fallacy is where in certain cases people hear a brief description of a person that involves a certain conjunction, and they assign a higher probability to the conjunction than they do to one of the two conjuncts. That's described in the Titelbaum chapter, so read that if you haven't yet. Now, Kolmogorov's axioms make it clear that the propositions involved can't range from most probable to least probable in a way subjects consistently rank them. Do you have any suggestions for why subjects might consistently make this mistake? Is there any way to read what the subjects are doing as rationally acceptable? Now, this is another one of those open-ended questions. There's lots of things that can be said. The one that generated an interest in the literature is just the flat-footed response. That's just stupid. It's never rationally acceptable to violate the probability axioms. Now, if you don't endorse that flat-footed response, you're going to look to see why people might be making this mistake. My own answer to this has to do with some of my work in epistemology, but here's what I would say. I'd appeal to the role of understanding in our thinking. Understanding is a systemic kind of success, whereas knowledge can be completely piecemeal. You can know a whole bunch. Think of being a master at Trivial Pursuit. So you know a whole bunch of individual pieces of information, but they don't hang together they don't need to hang together in any interesting or systematic way. Whereas if you understand, say, quantum mechanics, you probably don't. Even physicists claim nobody understands quantum mechanics. In any case, if you understand quantum mechanics, you understand how things hang together. Let's pick something that is at least capable of being understood. So think of the Comanche dominance of the southern plains of the US from 1775 to 1875. You can be a master of that period of history in that part of the world. You understand how and why things occurred. You understand who the relevant people involved are. You have a systematic grasp of a certain body of information. And as I understand the drive, which we call curiosity, it is a drive for understanding, not merely a drive for knowledge, because curiosity gets sated when you have a systematic grasp of things, not when you just learn a whole bunch of unrelated pieces of information about the topic. Okay, so if understanding is what drives our thinking, the drive toward making sense of things in a way that yields understanding, if that's what's going on with us intellectually speaking, there will be roles for scripts, or sometimes they're called frames, to play in such a process. So when you have an experience of a person or thing, let's just take people. Somebody engages in a bit of behavior and you are trying to locate that within some script or frame where you can make sense out of what the person is doing. And once you do that, you have this feeling of having come to understand the person in a way that you didn't before. So when you are told about a person or you observe a person, an individual doing something, you look for a script that fits and you reason from it. But scripts, remember, are going to be much more extensive bodies of information. So the description will be limited in a certain way. So suppose the story that you're given by Tversky and Kahneman identifies somebody as having both properties A and property B, and generally you don't see both of those properties going together. So you're looking around for a script, and maybe you only have a script for one of the two properties. And so that script is a pretty extensive one, and it's a kind of person, kind of property that you're quite familiar with. So you embrace the script as applying to the person as a result of some analogical reasoning from the story that you're given. And then you come to attach greater probability to the property that is attached to the script than to the conjunction of the property that's attached to the script with the other one that isn't. And that can be rational to the extent that this drive for systematic understanding is what's important, and the role that scripts and frames play in that. We can understand how the conjunction fallacy can be committed rationally. Okay, moving on, 211. Mr. Prob and Mr. Weak from section 4. Mr. Weak assigns lower credences to each contingent proposition than does Mr. Prob, while Mr. Weak's distribution satisfies non-negativity and normality. It violates finite additivity by being superadditive. It contains a disjunction whose credence is greater than the sum of the credences of its mutually exclusive disjuncts. Construct a similar credence distribution for Mr. Bold that instead of being superadditive is subadditive. It should contain a disjunction whose credence is less than the sum of the credences of its mutually exclusive disjunctions. So you add Mr. Bold at the bottom. Mr. Prob, Mr. Weak, and Mr. Bold, all three of them assign a credence of 0 to contradictions. They also assign a credence of 1 to tautologies. Now, Mr. Weak assigns probability to P and a probability to not P that sum to something less than 1. Mr. Bold makes the opposite mistake. He assigns a credence to P and a credence to not P that sum to something greater than 1. Mr. Prob, on the other hand, honors the probability calculus by assigning credences to P and not P that sum to 1. So there's a chart of how to construct Mr. Bold's distribution to satisfy the subadditivity constraint in the problem. That completes our discussion of chapter 2.